Alrighty, so welcome to my tutorial on digital delay lock loop design in SDRAM. My name's Eric Monahan, and I'm going to get started quickly. And it's not moving again. What the hell? It's doing the same thing. There it goes. Alright. So what is a delay locked loop? So I wrote a definition when I first started doing the project, but when I got further along and I look at it, it's kind of clumsy. So in simple terms, a DLL takes an input clock signal, inserts a delay through a delay element, and generates an output clock synced with the input clock but delayed in time by some integer multiple of the input's clock period. The goal is to have the output clock mirror the input clock in phase, magnitude, and duty cycle. So why do we want to use a DLL in synchronous DRAM? In short, the generated clock can be used to sync the output data with the system clock, which allows a high degree of predictability on when the output data will be accessible. That in turn allows us to increase our data transfer rates. And so, all right, I'm going to have to scroll apparently. So what is SDRAM? In a 30-minute presentation, I'm going to give you the Barney version of it. So recall, asynchronous DRAM uses RAS and CAS to clock strobes. So RAS and CAS signals can arrive at the DRAM pins at any given time. So basically DRAM uses timing to execute reads and writes. So now SDRAM uses RAS and CAS as command bits. They're executed on a synchronous clock edge. So for example, if we drive RAS high, it's a command signal. It's sent to a mode register with a decoder that executes the command and finds the row address. And that makes our RAS signal a command bit rather than a clocked in signal. So initially, SDRAM was single data rate, which means it was only transferred on the clock's rising edges. Later, they introduced DDR, which transfers data on the rising and falling edge. This effectively doubled the SDR data bandwidth. So, for example, if we had a 4 nanosecond clock period, it has a data rate of 4 nanoseconds, which is 250 megabits per second per pin. The same 4 nanosecond clock period using DDR gives us a 2 nanosecond data transfer rate, which is 500 megabits per second per pin. So the main advantage to DDR is twice the data rate without changing our frequency. Successive generations doubled the number of words that could be fetched per clock cycle. This doubled the bandwidth of the bus clock and the external bus rate while keeping the internal clock rates the same. This improved our overall efficiency. There's more trade-offs than that, but this is just a quick overview. I want to spend more time on the DLLs. One of the drawbacks is we have to sync the rising and falling edge of the clock to the changing data in order to achieve the higher transfer rates, and that's kind of what I'm going to do, talk about now. So, yeah, that button's not working. So now this is just a general DDR architecture. On the left is the DRAM architecture, and on the top right there's the additional circuitry for the SDR DRAM, and on the bottom it's the DDR. So the DDR architecture uses a pre-fetch buffer. This allows a single address request to fetch multiple words in bursts, and each word can go out as data or be masked by a DM signal sent out by the mode register. It's done by using internal data buses that are wider than the external data buses. And then something I'm only going to touch on briefly is CAS latency, which is the delay time between when the memory controller accesses a memory column and the time that the data actually comes out to the output pins. In SDRAM, this depends on the clock rate with the number of clock cycles that determine CAS latency programmed into the SDRAM mode register. And the goal of DDR SDRAM is to drive the data access time to 0 such that when clock goes high after the initial CAS latency period, data will come out synced with the clock at a fast rate. And then note the big red arrow pointing to the DQS generator. That's going to be important shortly because DQS is what allows us to sync the output data to the system clock. And I want to go through a quick example just to show how it works. This is a by 4 read, which just means it reads out 4 bits every command. If you focus on the top panel, at T0, read is high. We're reading from column N, and DQ has a latency of 2 cycles. If you look at DQ, we see data coming out from column N at T2, 2 cycles later, with data on both edges. The next read from column B is registered on the same T edge, and we see how at T4 the data from column B starts to read out. So in this manner, SDRAM hides the cast latency and allows data transfer rates to increase. We notice there's also a DQS signal in there as well. So basically, what is DQS and why does DQS matter? So if you look at this image, let's say we have some data being read out of the DRAM core. It goes to a D flip-flop or data register. This feeds to a driver. It goes to a pad we're going to call DQ, which is just a bidirectional data line, good for input and output. So if reads high and the driver's enabled and the DQ pad's driven, we're going to have some input clock signal, some data coming out synchronized, but with a finite delay between them. We want the data synced to the system clock such that data transfers at the same time as the clock on the rising and falling edges. This will give us our fastest data transfer rates. To this end, we're going to create a signal, DQS, which is DQ strobe. It's ideally a mirror image of the input clock. We're going to transmit DQS and DQ in parallel to our DRAM, and we're going to use DQS to strobe in DQ to give us minimal timing errors. This will also allow the maximum data window to be utilized. So the next step is going to be how we relate the clock to DQS. Alrighty, and if you look at figure 4, we're going to assume the DRAM is about to be read out through DQ, and there's some delay T2 through our flip-flop and driver on top. There's a clock with an added delay T1 through the D flip-flop and DQS buffer. We want the sum of these delays, T1 and T2, to equal T clock. So the total delay through the line is T clock, which is really what our goal is. We can do this if we make the delays through the DQS buffer and the DQ buffer and the D flip-flop the same. The result will give us a DQS and DQ that mirror clock by some integer multiple delay of clocks period. So you might ask why we need the delay T1. I kind of did when I was first going through it, and that's for process voltage and temperature variations, PVT. These can cause clock skew, and we want to be able to account for this to make sure that our DQS and DQ always align with the clock. And how do we do this? We use a DLL. So figure 6 below figure 4 is basically the same circuit with the DLL components added in, and I'm going to go into those components shortly. Figure 7 just shows the normal relation between the clock and the data. It varies due to PVT variations or changes in frequency. The goal of the DLL is to drive the access time, TAC, to 0 so the data syncs with our clock. And then before going into the individual blocks making up the DLL, I want to talk about some of the advantages of using the digital DLL. So first, the design uses a delay cell with minimum delay or resolution determined by a CMOS process. This allows us to quantify the delay. It locks quickly, it has a zeroth order transfer function, which makes it easy to stabilize. If the clock stops, DLL stays locked, so that if the clock jumps back in at at the same frequency, it's still going to be locked. If it comes at a different frequency, it'll have to reset. All right. Okay, so that's pretty much all the advantages I wanted to cover given our time. And I'm going to now go into our DLL basics. So on the left, those are the basic components. I'm not going to just read them off to you. One of the goals I had in the tutorial was to avoid covering the exact same material I saw in the previous people who had this assignment. But there's some fundamental concepts that kind of require repetition. So I'm going to go over our basic DLL circuit. This is an early register controlled DLL design. I'm going to go through the components individually later. Now, in an ideal design, the phase detector is going to maintain a delay around the loop so that it's equal to n times t clock. N is just some integer multiple of the clock period. And why do we want to do that? We want our PD to compare the feedback signal to t clock and be the same. So the PD and shift register control the insertion point where we inject the clock into the delay line. This is something that really confused me when I was first learning about this. I finally kind of figured it out, and I'll go into detail on it when I talk about the shift register. All right, a few slides back, I determined we want t clock equal to the sum of the delay elements in the clock path when we said t1 plus t2 is equal to t clock. Here, our delay elements are TIB and TD, so they're the same basic thing. We want t clock equal to TIB plus TD. So our input buffer and output buffer are subject to PVT variations. So the DLL is designed to remove these variations by introducing a delay model in the feedback path. This effectively allows the phase detector to track the variations closely. And to maintain a loop delay of t clock, we're just going to subtract the feedback delay from the delay line such that it has a delay in t clock minus TIB plus TD, What this basically did is we put it in, we're just taking it right back out. We still have NT clock in the ideal case. But nothing's ideal. There's going to be variations between our input buffer and our output buffer and our feedback delay model. They're not going to be exact, and that's going to limit how well the DLL models and N times T clock around the loop. And then before continuing, I'm going to go into some design considerations. We already talked about PVT variations, so false lock. The DLLs are prone to locking on at different harmonics for the same clock period. It can be difficult to detect. So to avoid locking on different harmonics, the minimum time delay should be kept to 0.5 T clock and a maximum of 3/2 times T clock. Ideally, this will prevent the rising and falling edges from aligning with the wrong harmonic when they get too close to a different. There's a number of papers that have different design solutions that minimize or eliminate false lock, and I'm going to cover one of those later. The duty cycle, we want our output clock to have a 50% duty cycle, even if our input clock isn't 50%. This provides the most consistent data window availability for the SDRAM data transfers. And then jitter, Dane covered that the other day. Describes the amount of time the feedback clock varies compared to our reference clock after the loop locks. So the nature of DLLs using a cascaded delay line, it introduces the potential for jitter amplification from input to output. So we use jitter performance as a pretty important metric in design. And now I'm going to roll on to the components. So our input-output buffers, we covered these in class a bit, so I'm just going to touch on them. So the goal of the input-output buffer is to look at a circuit's input signal and convert it to a clean digital signal. Inverters aren't used for the input buffer because the switching point VSP changes with PVT variations. It changes our output signals bit width because the input signal is not sliced down the middle. I don't know if you all remember that from class. That's not good. So an example input buffer seen in figure 9, it's figure 1823 from our textbook, a rail-rail input buffer that compares the differences in the signals and generates a skewless output. The buffer self-biased, so it depends on inputs only for adjustments. There's no external references for setting the current, which makes it more efficient as well. And the output buffer is just an even number of inverters. We've covered these in class ad nauseum. So we can use these because the delay model and the feedback compensates for the PVT variations. And the feedback delay model literally, it just puts these two in series to model their delays. I'm going to move on to the phase detector, which we've also covered in class. We're all familiar with the basic idea. These function as the logic of the circuit by comparing the phases of clock in and clock out and determine if the shift register needs to shift right to reduce the delay, shift left to increase the delay, or do nothing. And this clock in is our reference clock out's the feedback clock. And this phase detector has a divide by 2 to clock the output every 2 cycles. This allows enough time for the shift register in the next stage to adjust the delay. And now we'll get into the voltage controlled delay line. So the basic delay element is a NAND pair with a PMOS and NMOS, each NMOS gate tied high rather than an inverter string. And the primary reason for this is that NAND provides a constant delay because one's always going low to high, one's always going high to low. But the NAND allows us to inject the clock into the delay line where the inverter is unable. And one of the drawbacks to this design, though, is it's the delay is only adjustable by the inherent delay of the NAND pair, and this is where our resolution starts to come into play. So, for example, if we have a NAND gate with a delay of 50 pico, 2 of them together, it's going to be 100 pico. We're only going to be able to adjust the line in those 100 picosecond increments, which is kind of a coarse delay. There's applications that might require a better resolution, so for these cases they can add a fine delay element, and that's what's in figure 13. It's a shunt capacitor inverter delay, and it uses a MOSCAP network connected to the input inverters using NMOS switches. You select pins A1 to AN to change the load. This changes the rise and fall times of our inverted input signal, and it passes back out through the output inverter, but now it's delayed by the fine delay element. This SCI design claims to achieve a 1.43 picosecond delay, which is pretty tight. And it's common to see designs with both a coarse and fine delay, where the coarse delay is going to set the loop near lock, and then the fine delay is going to be used to tighten it up. So now I've covered everything except how the shift register injects the clock into the delay line. So let's do that. All right, so DLL circuits will typically initialize the shift register with some initial delay amount. Ideally, the registers are initialized with all zeros and a 1 somewhere in the register. and a 0-1 transition is used to inject the clock. The delay can be anywhere in the register, but modern DLLs will usually put it in the first location because there's so many parts in the clock path that the delay between input and output data is longer than a single clock cycle. So initially we're just adding delay. And for me, I had a hard time, or I always have a hard time looking at stuff like this and intuitively understanding how it works. So while I was doing this, I broke it down step by step, and that's how I'm going to kind of explain it, see if it makes sense to you. So note, there's an additional NAND added to each delay element to eject the clock along with our NAND pairs. If we assume the shift register entry point's on the right and the first low to high transition serves as our entry point for the clock, how does it work? So the high block has a 1 at Q and a 0 at Q dash. Q dash locks one of gate A's inputs to 0, so no matter what the other input is, gate A will output a logic 1, if you look at the NAND table for reference. So effectively, any incoming signals from the left are irrelevant since the output of A is locked to a 1. So the next thing, Q locks one of gate B's inputs to 1. The other B input is tied to clock, which ensures the output of gate B will toggle with the clock between 0 and 1. B output feeds gate C. It's the same situation, has a leg locked at 1 from the input of the output of A. So B's output toggles, so will C's output the same. And we can replicate clock transitions this way, plus some delay. Now, by keeping the blocks to the right low and tying all the Q dashes to 1, we lock a logic 1 to each successive NAND, and this ensures the clock passes through the delay line. You can see the red arrows show where the insertions, that insertion point is, and how the signal propagates, and delay can be added or subtracted just by adjusting our insertion point. And that's pretty much how it works. Does everybody understand?
Yes.
Does anybody understand? All right, so delay lines. So the basic example we went over used a shift register, but there are other alternatives to a shift register. So the counter control DLL uses binary weighted delay elements and an up and down counter to control the amount of delay based on the PD output. The resolution of the delay is tied to the linearity of the delay line. Binary weighted delay elements maintain a fixed binary weighted linearity. Our TDC, time to digital converter, it abandons the feedback method we covered in favor of a digital approach by converting the input clock period into digital code. This DLL separates the locking stage into 2 stages, phase compensation and phase tracking. Phase compensation uses the TDC to measure the period, send an output code to a controller, and the controller position itself along a delay. The phase tracking stage then steps in and uses the PD to tighten the delay and lock in. So this avoids false lock by setting the delay line to a minimum during the phase compensation stage. And the next thing I'm going to cover is the SAR. This is what I'm going to spend the rest of the time on. It uses the idea that a DLL's basic operation is a sequential search. So the loop searches for the best delay and inserts the delay between the input and output clocks. It uses something called a binary search algorithm to reduce the search time using an n-bit SAR register that takes only n cycles to lock in. And binary search is an algorithm that finds an item from an ordered list of items by successively dividing the list in half until it narrows down all the possible locations to a single one. These are still widely used today, these types of DLLs, and the more I read about them, the more interested I was in them, so I'm just going to focus on a single SAR design that I thought was kind of interesting to contrast the basic design we covered earlier. So it's going to be a quick and dirty synopsis given our time constraints. So up top we see we have a binary weighted delay line. Each delay is twice as long as the previous delay, with bits B0 to B2 used for fine delays and B3 to B5 for coarse delays. Individual delay element is seen on the bottom. That's an individual cell. They're designed to employ interpolation, which is estimating basically, and it preserves the clock's 50% duty cycle. It's done to account for differences in low to high and high to low transitions, which is similar to why we used NAND pairs earlier. It does so by comparing the different delay times of the 2 paths. So in this cell, the control input 0 basically means there's too much delay, dial it back and take the fast delay path. If the control's a 1, we're just going to add more delay and slow it down. Alrighty. So to get into the basic SAR operation, I'm strictly going to focus on how the SAR functions, not necessarily this circuit. This is just a sample image. So the SAR is a multiple input shift register made up of positive edge triggered D flip-flops, a decoder, and a multiplexer. So to initialize it, the bits in this 6-bit register are set to 1, 0, 0, 0, 0, 0, which sets the initial delay to half T clock. That's the first part of our binary search algorithm, it's half. Then the logic 1 is in register 6, and this serves as a coarse compare signal that tells, that compares the initial delay with our clocks. Next, the phase detector will compare the signals, and let's say the feedback clock, DQS, is going to lead our input clock. Then the compare signal is going to be 1, meaning we want a larger delay, so the feedback tracks clock in tighter. This will load into register 5, the 1, and now we have a control word of 1, 1, 0, 0, 0, 0, setting the delay to 3/4 T clock, which is the second step in our binary search. Half, again, it adds half. So next the PD will compare again, and let's say our clock in leads feedback clock now. Then the compare signal is going to be 0, and it's going to load into register 5. This is basically telling the line that the excess delay we just added was too long, we need to dial it back. And at this point, the 6D flip-flop goes into a memory mode. The other flip-flops are all shift right, and kind of in this manner, the SAR continually guesses a digital word until the proper delay is determined and a stop signal is executed by the controller. And that's the basic premise for a SAR-based DLL. So now I'm just going to go into a different DLL design that uses a SAR and claims to eliminate false lock and control duty cycle. So this is a design I found from 2012. I had found a more recent paper, 2015, but they did a really horrible job explaining it, so I found this one, which was much simpler. And it uses what the designers call a novel complementary delay line as a second delay line that reduces the number of active elements, giving a wider, also giving a wider lock frequency range than a single delay line offers. It also allows for the SAR to be used as a conventional shift register, a SAR, or a counter, depending on what stage of operation the DLL is in. And due to this, it uses 2 PDs, which is necessary to count for the different SAR modes. The key design features are a complementary clock select unit, a delay range search unit, and a complementary delay line, along with a find delay line. So how does it work? I am glad you asked, because I can't wait to tell you. So the circuit is on the right. The goal is to choose either of 2 possible feedback clocks, clock or clock B, which is just the inverse of clock, and these are generated by our complementary delay lines. So the CSU chooses whichever one provides the least amount of delay between the edges of the reference clock. This is supposed to decrease lock-in time and reduce the number of active delay cells required to lock, which makes it more efficient as well. In a quick example, if you look in figure A, we can see the phase change between clock in and clock out is less than 180. That's indicated by T0 between the rising edges. Below that's the complementary feedback clock. I added that in actually with delay T0 dash between the edges. T0 dash is less than T0, so the unit would select the complementary clock for phase differences less than 180, and then the opposite is delays greater than 180, it will choose clock, which is the basic idea of the first stage of the design. So I'm going to move on to stage 2, which is the delay range search. And this uses something called the delay range search algorithm to find the proper SAR bit to avoid false lock, with the proper bit being a spot in the SAR that ensures a phase difference less than 360. It uses a couple divide by 2s to eliminate the duty cycle distortion, where flip-flops D0 and D1 sample each other on the rising and falling edges, which ensures we have a 50% duty cycle out regardless of what our clock-in's duty cycle is. And before the SAR locks in, the delay range search tracks each cycle of the SAR's iterative search process, and the SAR is acting as a shift register, which is controlled by a MUX. And the best way to describe how this finds the optimal SAR bit is to look at an example search operation. So in context, we know divide by 2 clocks result in twice the period length. So our divide by 2 clocks will have twice the period length of our clock in and clock out. So half of the divide by 2 clocks are equal to the full 360 phase of clock in and our feedback clock. Looking at the kth SAR cycle, if the rising edge of clock out divide by 2 comes before the falling edge of clock in divide by 2, the phase is less than 360. And we know this because the half period of clock in divide by 2 is 360-degree phase difference relative to our input clocks. The unit will send out a 0 and to the SAR to tell it to keep searching because our phase is less than 360. Then on the K plus 1th cycle, the rising edge after the falling edge, meaning the phase difference is greater than 360, so the unit sends out a 1 telling the SAR to stop searching. and use the kth bit as the optimal delay. That's stage 2. Now we found the optimal delay bit, and in stage 3, the mux is engaged, and the SAR stops acting like a shift register, acts like a SAR and locks in, which I covered earlier. So I'm going to move on to the delay lines. And these are, so what they did was they took a conventional cascaded NAND delay that's in figure A, and it has a 2 NAND gate delay. They modified it such that it uses 6 NAND gates to create parallel coupled delay lines with a 180 degree phase difference. This generates 2 delay lines that allow for the complementary clocks selected by the CSU in the first stage. These lines feed to a 2-input mux. The CSU generates the mux select signal, and that sends one of the clocks to the phase detectors. And then in figure B, we see enable signals. These are generated by binary to thermometer decoders that'll track the PVT variations. I think I had those right here. I don't want to get myself too far behind. But basically, these control the logic along with a constant 1 tied to the upper line, a constant 0 on the lower line to ensure the clocks are complementary. And then the fine delay cell uses a fixed inverter and 3 additional inverters controlled by enable again. And the designers claim this has a resolution of 8 picoseconds, which is also pretty tight. And then moving on to the next slide, the last thing I'm going to talk about is the 9-bit SAR that they use in this. So recall I said the SAR can function as a shift register, a SAR, or a counter. Muxes control the shift register behavior, but the ability to transition to a counter is a little more complex. So in this picture, the start step 2 signal on the top left functions as a select signal, which feeds a mux. We have an enable signal that's fed back through a series of 2 input AND gates on the bottom, dependent on the flip-flop Q signal and the output of the previous stage. So if select is high, it functions as a shift register. That's pretty simple. So if select's a 1, it's a shift register. But if select is low, enable is going to control whether the SAR acts as a counter or as a SAR. This is an individual SAR cell. If enable is low, it's a SAR. If it's high, it's a counter. It's that simple. And this is how it toggles between locking in as a SAR or tracking PVT changes as a counter. And in this cell, UI and DI are up in and down in, and these represent the propagating phase detector comparisons feeding into the SAR. The combinational logic determines if the up-out or down-out signals go high or low, thus incrementing our counter or not incrementing it. And when the UI-DI inputs are 0, 0, or 1, 1, our output's always going to be a 1, and there's going to be no count operation. If the inputs are anything else, the counter moves up or down depending on the Q, which is feeding back. Q and Q bar feed back into those NOR gates up top. That's pretty much it for the whole design. That's what I found to be the most relevant details that I have time for. So the designers ran some sims that show a comparison of their design versus single delay line, and theirs results in reduced lock-in and half the number of active delay units, so it's more efficient. And in the end, this allows the DLL to efficiently align our output clock, DQS, with our input reference clock, strobe DQ into our theoretical SDRAM as intended. And that pretty much concludes my presentation on digital delay lock loop design in SDRAM. I will mention quickly before I open it up to questions. This is Robert H. I'm not sure if it's Dennard or Dennard, but he's the inventor of DRAM. Invented in 1966. He worked at IBM. He's got some serious IEEE Medal of Honor winner 2009, Edison Medal 2001. I don't know what those are, but they sound impressive. But I mean, it's a pretty big deal, and it's just my way of paying homage to the giants who came before us, and thought it'd be kind of cool to throw that in. So open it up to questions.
Thank you. That's my buddy Bob.
Have you met him?
Yeah, I went to the Franklin Institute and 10 years ago and gave a talk in Philadelphia for him.
Okay.
So,
Yeah.
he won a Franklin Award.
Okay.
Do you know anything about the Franklin Institute?
I don't know anything about the Franklin Institute.
You live there.
No.
What is it? Who's it named for?
I'm assuming Benjamin Franklin if it's over there.
What's the benefit of Ben Franklin, or what's Ben Franklin's notoriety?
He defined positive and negative. He discovered
First
electricity.
electrical engineer.
Oh, okay, there you go.
All right, before I ask my questions, does anybody else have questions? I prefer other people's questions. All right, I got questions. for you.
Okay, yikes.
We talked about the digital DLL at the beginning.
Okay.
What does zeroth order mean, or zero order transfer function?
Means it has no poles in its feedback. Is that kind of the simple way of
Well,
looking at
even
it?
simpler.
Zeroth order. There's no active. What am I thinking of? There's like no capacitors, no.
Well, it just simply means whatever the error is, you get the exact same response. So if the phase shift is this, you get an up or a down, or if it's like this, you get an up or a down. It's the same response. It's like one tick up or one tick down, or shift right or shift left.
Okay.
There's no significance to the magnitude of the error. You get the same response when there's error.
Okay.
What does SAR stand for?
Oh, successive approximation register.
Yeah, well, can you explain to us what that means? What is a SAR?
What is a
Yeah,
SAR?
I want to know what it is in simple terms.
Simple terms.
Yeah, I'm John Doe here
Okay.
on the street at
So,
the supermarket.
The way I understand it is that it's a successive approximation register uses, if it's an n-bit register, for example, we're gonna have 10 bits. And the goal is that it's gonna use those 10 bits, this is where the binary search algorithm comes in, which finds something by continually dividing something in half. So it'll use 10 approximations to narrow down the search looking for the perfect delay range.
If I tell you to guess a number between 1 and 100, how would you use SAR to guess the number? in
You're going to
10
compare
guesses?
greater than or less than, I guess. You say.
Yeah, how would you use SAR, the excessive approximation register?
So I would guess 50, and then I would say, is it greater than or less than, by
And then
comparing
I'd
it.
say, okay, it's greater than.
And then I would
say,
add
I would
25.
say is it greater than or less than 75?
Right, and then I would, so forth, right.
And that's how you pull it in tight in the SAR DLL.
Right, so that would have been what's lacking from my explanation. Okay.
I mean, I just want to make sure, I mean, if you know what SAR is, it's easy. If you don't know what SAR is, then you're like,
Right.
what the hell's SAR?
Which is actually why I picked it, because when I was first reading about it, I was absolutely lost. And the more I read
You know
about
what SAR
it,
is
it's
if
cool.
you take advanced analog.
Yay.
Other questions now that I've broken the mold on questions? Wisdom. Dan, you're done. You can't do it. You're being harsher than all of you.
I like that. It's a question for both of you, I guess. But so with the SAR, does it take maybe like too long of a time, or like how long of a time? What's the delay time for if you're guessing in successive approximations? If you guess like between 1 and 100, if you're guessing 50, then it's going to take a little. It's going to take a couple
Well,
approximations.
it's based off the number
Is that
of
really
bits.
the delay?
The way I understand it, it's based off the number of bits in the register.
Okay.
So however many bits you have is however many guesses it's going to take.
Uh-huh.
So 10-bit register, 10 guess max, 10 clock cycle max,
Right.
6-bit register, 6 cycle max. That's the way I understand it.
Good answer.
Cool. So the more bits is going to
Right.
longer approximation. Okay.
All right, any other questions?
So the number of bits corresponds to the maximum range you can lock onto, right? Frequency?
That's a good question. I'm going to say the number of bits, that's got to be based on your delay line, so I got to say it would be. Because your range is going to be based on your delay line, I believe. So in the novel complementary delay line, the one I covered, they claim it makes it a wider range because it adds a second delay line, which expands its frequency. So if I think of it like that, I would think that would be a yes.
That makes sense. That's the trade-off. Larger range for longer time.
Longer time delay elements. So, okay.
All right, any other questions?
Good.
All right, let's thank our speaker
Sweet.
again.
I was stop
Press
at
F10.
F10.